Welcome to Sri Learning Academy. Let's simplify atomic operations in OS. Ever wondered how an operating system prevents complete chaos when many processes try to update the same data at the exact same moment? Imagine two threads trying to book the last movie ticket online, or two ATM requests trying to withdraw money from the same account balance. If both actions happen together without control, the result can be wrong, inconsistent, and sometimes disastrous. This is exactly why operating systems rely on something called atomic operations. These are tiny but powerful hardware supported actions that happen as one indivisible step. No other process can interrupt them halfway. In synchronization, atomic operations become the foundation for building locks, mutexes, semaphores, and many safe coordination mechanisms that we will study next. To understand atomic operations, think of the word atomic as meaning unbreakable into smaller visible parts. In everyday programming, a statement may look like one line, but internally it can involve multiple steps. For example, if we write counter equals counter plus 1, the CPU may first read the value, then add 1, then write it back. If two threads do this simultaneously, both may read the same old value and overwrite each other's updates. This creates a race condition, which we discussed earlier. But if the increment were atomic, the entire read modify write sequence would happen as one protected action. No other thread would interfere in the middle. That is why atomic operations are so valuable in operating systems and concurrent programming. You can imagine a bank locker room with only one master access point. If one person enters and locks the room, nobody else can partially enter until the first person exits. That complete entry and exit sequence behaves like an atomic action. In computing, the CPU or hardware provides special instructions so these operations happen safely even when many processors or cores are active at the same time. Without such hardware support, synchronization would become slower, more complex, or sometimes impossible to guarantee correctly. One of the most famous atomic operations is test and set. The name itself explains the behavior. First, it tests the current value of a memory location. Then it sets that location to a new value, usually true or 1, and returns the old value. The key point is that both actions happen together atomically. No other thread can sneak in between the test and the set. This simple instruction is often used to implement locks. Let us understand test and set with a practical example. Suppose there is a shared variable called lock, initially set to 0. Here 0 means unlocked and 1 means locked. When a process wants to enter the critical section, it performs test and set on lock. If the old value returned is 0, that means the lock was free, and now it has been set to 1. The process successfully enters the critical section. If the old value returned is already 1, that means someone else holds the lock, so the process must wait and try again. Imagine two people reaching a meeting room door at the same time. The door has a smart signboard. The first person who presses the button sees free and instantly changes it to occupied. The second person presses immediately after, but now sees occupied, so they wait outside. That is exactly how test and set protects a critical section from simultaneous access. However, test and set also introduces an issue we touched on earlier called busy waiting. If a process keeps repeatedly checking the lock in a loop, it wastes CPU cycles. It is like standing outside a washroom and rattling a handle every second instead of sitting down and waiting calmly. This is why test and set is commonly used in spin locks, where threads spin in a loop until the lock becomes free. Spin locks can be useful when the waiting time is extremely short, especially inside kernels, but wasteful when waits are long. Another very important atomic operation is compare and swap, often written as CAS. This instruction is more flexible and widely used in modern systems. Compare and swap checks whether a memory location contains an expected value. If it does, the instruction replaces it with a new value. If not, nothing changes. Again, the whole check and update happens atomically. Let us make that simple with an example. Suppose a shared variable x equals 5. A thread performs compare and swap with expected value 5 and new value 9. Since x is currently 5, the comparison succeeds and x becomes 9. Now imagine another thread tries compare and swap with expected value 5 and new value 12. This time it fails because x is no longer 5. Since the comparison fails, the value remains 9. This may sound small, but it is extremely powerful. Compare and swap allows a program to say, only change this value if nobody else changed it since I last checked. That makes it ideal for concurrent updates. Think of editing a shared online document. You save changes only if the document version is still the one you opened. If someone else edited it first, your save is rejected and you must refresh. Chaos follows the same logic. Compare and swap is heavily used in lock-free data structures such as queues, stacks, counters, and reference management systems. Lock-free means threads can coordinate without traditional locks in some cases. Instead of blocking each other, they retry safely when conflicts happen. This can improve scalability on multi-core systems because threads spend less time waiting. Many modern programming libraries internally use CAS even if the programmer never directly sees it. Now let us compare test and set and compare and swap in a practical way. Test and set is simpler and mainly used to acquire a lock by marking it busy. Compare and swap is more general because it checks for a specific expected value before updating. Test and set often works well for basic spinlocks. Compare and swap works well for more advanced synchronization where values may change frequently. If test and set is like flipping an occupied sign on a room, compare and swap is like changing the sign only if it still says what you expected. There are still limitations. Atomic operations solve the low-level update problem, but they do not automatically guarantee fairness. One thread may repeatedly win while another waits. They also do not prevent deadlock by themselves if higher-level logic is poor. In addition, on highly contested systems, constant retries can reduce performance. So while atomic instructions are powerful tools, they must be used carefully within well-designed synchronization strategies. Inside operating systems, these instructions are everywhere. Kernels use them to manage scheduler queues, memory reference counts, process states, interrupt safe logs, and shared counters. Even when you open apps, switch tasks, or access files, atomic operations may be quietly maintaining consistency in the background. They are small instructions with enormous responsibility. So the big picture is this. Atomic operations are the hardware-backed building blocks of synchronization. Test and set helps claim locks safely. Compare and swap helps update shared data only when conditions match. Both prevent dangerous mid-operation interference between concurrent threads or processes. In upcoming topics like hardware synchronization solutions, semaphores, mutexes, and monitors, you will see these ideas grow into full coordination systems. But at the core of many of them lies one simple principle. Some actions must happen completely, or not at all. That is it for this video. See you in the next one.